Okay, now on to part F. So if we're still in the short run, suppose that Duke can sell electricity for $5 per unit. Question asks, will we make a profit if we sell 100, 1,000, or 5,000? So we need to check all three of these quantities and see if any of them are profitable for the power company in the short run. So what we want to do is just set up total revenue. So total revenue is going to be $5 times quantity. And so that's very easy here. If we have 100 megawatts, the total revenue will be 500. If the output is 1,000, then the total revenue will be 5,000. And if we're selling 5,000 units, then the total revenue will be 25,000. Now we need to figure out the total cost for each of these three output levels. So now we go up to our total cost function here is one way that we could do this. So, or we can use this version here. So let's just calculate our total cost. Now our fixed cost is going to be the same for all three of those output levels, $1,600. So we can answer some of these questions right now. So total revenue minus total cost. So $1,600 is the fixed cost in each of these three cases. So we can already tell that we are not going to be able to make a profit in this first case where we're selling 100 units because our fixed cost is bigger than our total revenue. So that's pretty clear that we will not be making a profit here. The other two, we're not sure yet. So what about if we're selling 1,000? Well, actually we already calculated the total cost for 1,000 up here. The total cost we figured out would be $2,000. So we already know that the fixed cost was here for 1,000 units, that the fixed cost was 16 and the variable cost was 400. Now let's figure out the total cost for 100 megawatts. We can just kind of all do these at the same time. So let's plug in 100 into this total cost function here and see what our variable costs are going to be. So we're going to get 0.000004 times q squared, sorry, q cubed. So 100 cubed times 0.000004 equals. And the variable cost for producing 100 units is going to be very low. It's only going to be $0.4. All right, and so let's figure out the total cost of producing 5,000 by plugging 5,000 to figure out how much our variable costs will be there. So 5,000 cubed times 0.000004 equals $50,000 there. So $50,000. Okay, so are we going to be profitable in any of these three cases? Well, in case one, clearly not, because 500 minus $1,600.40, we're going to end up with a loss here that's going to be quite large. I think it's going to be, what, $1,100.40 loss. In this case, our total revenue is 5,000 minus 2,000 in costs. So yeah, we will be able to make a profit. We'll be profitable at that output level. $3,000 profit. And then here at the high output, we're going to be in losing territory again, because even though our total revenue is high, our total costs will be much, much, much higher here. We're going to lose, it looks like, $26,600. So $26,600 loss. And so this just shows you that you can be profitable at some ranges of output and not profitable in other ranges of output. Kind of makes sense when you think about it. Okay, so let's look at the second page of our sets of problems here. Let's look at the long run situation. So here is a set of isoquants for this production function here. So in the long run, let's find the optimal level of fuel and capital that you would want to produce 100 megawatts. So what we want to do is, in the long run, when we can adjust our capital, it's not fixed at 100 anymore, how much capital would we want? And then let's do the same thing for 1,000 and 5,000 megawatts. So in order to do this kind of cost minimization problem, we want to look at two equations and two unknowns. Our two unknowns are how much fuel and how much capital. And here are what our two equations are going to look like. This is very similar to what we did when we were looking at utility maximization. We did a similar kind of problem a couple of times. But our two equations we're going to be dealing with are, first, we know we're minimizing costs whenever the marginal rate of technical substitution is equal to the ratio of the prices. So here we're looking at the price of fuel over the price of capital. So that's one of our equations. And the second equation we're going to look at is the production function. We have to guarantee that our production function is equal to either 100, 1,000, or 5,000. So Q equals 100 or 1,000 or 5,000. And we just have to write down what our production function actually was. So replace the Q with F to the 1/3 times K to the 2/3. Because now we're letting the amount of capital and the amount of fuel be variable. So now we just have to set up these equations and solve three quick problems here. So you pause the video and see if you can do it, and then come back and we'll check our answers. I just wanted to point out before you got too far, I'm sorry, this is the production function again is 10 times F to the 1/3 times K to the 2/3. So make sure you use that. So now pause the video and come up with your solutions for these three answers, and then we'll check them. Okay, so the marginal rate of technical substitution function you can get by dividing the two marginal product functions, or you can use the simple rule for Cobb-Douglas production functions. You're going to end up with K over 2F, very simple there. So that's this part of the equation, and then the ratio of the prices is 4 over 16, or 1/4, so you can simplify that here to 1/4. So simplifying this equation here, I got either K equals F over 2 or F equals 2K. Either way you want to do it. And then just substitute one of these two relationships into the production function up here. And so I substituted F equals 2K into the production function right here. And that production function simplified down into 12.6K equals Q, or K is going to be equal to whatever the quantity of output is divided by 12.6. Using that, along with the relationship that we're going to use twice as much fuel as capital, because F equals 2K, we get these three answers. For 100 units of output, K equals 8, F is 16. For 1,000 units of output, K is 79.4, F equals 158.7. I rounded the 8 and the 16. These are actually 7.9 something. And then for 5,000 output, again, kind of rounding, K is about 397, and the amount of fuel is about 794. And so if you wanted to draw these on this isoquant field here, then what we could do is use the fact that the price of fuel is 4 and the price of capital is 16. And if you wanted to draw the ISO cost, what we would have to do is take one of these. For example, let's see if we can do this intermediate answer here and draw the ISO cost. We'd have to figure out how much it costs to buy 79.4 capital and 158.7 fuel. So let's just do that real quickly. 79.4 capital times 16 is going to be about $1,270 plus add the fuel, 158.7 times $4 for fuel. And the total cost here is about $1,905. So $1,905 is the total cost of producing 1,000 output. Now we need to figure out like a budget line. Except we call it an ISO cost when we're in production terms here. So in order to figure out what this budget line or ISO cost is going to look like, go back to what we did with budgets and utility and just figure out if I had $1,905 to spend, how much fuel could I buy if I spent all my money on fuel? Well, 476.3, and so we're kind of off the scale here. Let me figure approximately where that would be. 300, about 350, 400, about 450. Okay, somewhere in this neighborhood over here. Then how much capital on this axis could we afford if we spent $1,900 on that? So 1905 divided by 16, we could afford only about 119 units there. So somewhere in this neighborhood right here. And if we connect those two lines, this is going to be very challenging to make a straight line that's this long, but let me do my best. Okay, well that's fairly straight-ish. Assuming that was a straight line, then that would tell us that this is the ISO quant for 1,000 units running through here. And we've just found where the slope of the ISO cost is equal to the slope of the ISO quant, if you wanted to just double check your answer. And if this is the right answer, then it should be approximately where our optimal solution was. This is the point of doing this, of about 160 fuel, yeah, a little bit more than 150, and about 80 capital. And sure enough, that looks like that could be about right to verify our solution there. All right, let's see what's next here. Given our answers in G, calculate the total cost and average total cost for producing these three levels of output. Well, we calculated the total cost of producing 1,000 right here, $1,905. So if total cost is $1,905, then the average total cost is just divide it by quantity. So average total cost, divide that by 1,000. So that'd be $1.90. Right, or 1.905. For producing 100, the total cost is going to be, just plug in, calculate the cost for buying 8 capitals and 16 fuels. And what you're going to find is that that total cost is $190.50, and the average total cost is going to be the same, I believe. Let's check that to make absolutely sure that I'm telling you the right thing. So 8 units of capital, 8 times 16 equals $128, plus 16 units of fuel times $4 each, $192. Yeah, except for a little bit of rounding there, that's right. If you don't round those the K and the F, we don't actually need exactly 8, a little bit less than 8. So the average total cost is going to be about the same thing, about $1.90. And same thing for 5,000. You're going to find that the total cost happens to be exactly 5 times that amount to produce 5 times the amount of units. So why is this? Well, the reason why the average total cost is staying the same in the long run is because this production function we're working with has constant returns to scale. And so with constant returns to scale, that means that when you increase output, as long as you're talking about the long run and you can increase the capital and the fuel, that your average total cost is not going to go up and it's not going to go down. So use H to compare with F. So here we found that our average total cost doesn't go up, so we have constant returns to scale. Go back and look at F when we were talking about what happens in the short run when we increase our production. Well, here when we increase our production in the short run, we are not able to take advantage of those constant returns to scale. And here you see when we increase our production, our cost per unit is really increasing a lot when we're not allowed to vary our capital and we can only change our fuel. If it was true that our cost per unit was only $1.60, or what was it, $1.90? Yeah, if our cost per unit was always $1.90 in the short run here, if we were able to sell our electricity for $5, the price is $5 per unit. As long as the average total cost is always $1.90 per unit, we're always going to make a profit in the long run if we can make those long run adjustments, but not in the short run. So this is one way that we can say legitimately that if a firm is losing money in the short run, they may be able to make some adjustments to lower that average total cost in the long run by adjusting their capital and labor or whatever their other variable input is to making that efficient. Okay. J, suppose Duke Energy had a budget of only $2,000. Let's look at this question. Suppose that they just didn't have as much money as they wanted to, but they just had to produce as much output as they could, and they only had $2,000 to spend. How much capital, how much fuel would they use, and how much output could they produce hypothetically if they could adjust their capital and their, well, not labor, we're assuming that our variable input here is fuel. What do we do? Well, this is precisely like maximizing utility subject to a budget constraint. So to do this, what we're going to do is we're going to take what are our two equations and our two unknowns going to be? Well, one of our equations is going to be F equals 2K, marginal rate of technical substitution equals ratio of the prices. So let's just write that down there as one of our equations. F equals 2K. That's basically saying the slope of the budget line equals the slope of the indifference curve. Or since we're talking about production, the slope of the ISO cost equals the slope of the ISO quant. Our other equation that we're going to use to solve this kind of problem, the other equation is going to be that we spend all of our money, just like when we were doing utility kinds of problems. So how do we spend all the $2,000? Well, it's $4 times the amount of fuel plus $16 times the amount of capital has to equal $2,000. And so these are going to be our two equations. So what do we do? Well, we can find F here, substitute in for 2K. What we're going to have is 4 times 2K, or 8K, plus 16K equals 2,000. So we're going to have 24K equals 2,000. 2,000 divided by 24. In this case, we would want to use 83.3 Ks. We're going to use twice as many Fs. So multiply that times 2, and we get 166.67. 66.7. We can just round it off there. Fs. And how much output are we going to be able to produce here? Plug these back into that production function, which is F to the 1/3. So 166.67 83.7 to the 1/3 times 83.3 to the 2/3, and see how much output we're going to get there. And this will be our last calculation. So 166.7 raised to the 1/3. I get 5.5 times 83.3 raised to the 2/3. I get 104 or 105 here. So multiply those two together, and oh, we don't get 105. Sorry, my calculator did the whole answer. What that's going to give us is 105 units of output. 105 units of output. Now let's see if this answer makes sense. Let's compare it to our answer when we had 100 units of output up here. With 100 units of output, we were going to use 8K and 16 Fs. Oh, this is 80. Oh, I must have hit the wrong key. Hold on one sec. Oh, I understand. I keep forgetting with our production function that the production function is 10 times F to the 1/3, K to the 2/3. So when you multiply it times 10, sorry, we're going to get about 1,000 units of output, which actually makes sense because up here, when we had 1,000 units of output, it costs us $1,905, right? Here we're producing a little bit more. We're actually producing 1,050 units of output, so it costs us a little bit more, $2,000, and we're using a little bit more of our inputs than we were when we were producing 1,000 units of output up here. Instead of 79.4 and 158, to produce slightly more output, we're using slightly more of our inputs. So that's a review of some of the things that we were doing with production. I hope this helps. If you have any questions, please let me know, and I'll be happy to try to answer them.